Alright, in this video we are going to enhance our draw scaling system. Now, if you remember from the last video, we had already tested it out and everything seemed to be working just fine.
Technically, it is fully functional. It has only one small problem that would really only begin to arise as you started to pass your game around to a lot of different people.
And that problem is differing aspect ratios between displays.
Yeah.
Of course, on modern displays, you can go from things like a 4:3 aspect ratio computer monitor over to a new and fancy LCD that has a 16:10 aspect ratio, over to a high-def television that has a 16:9 aspect ratio.
Right.
And at the moment, you might be wondering and thinking, well, still, that's why we wrote the draw scaling system, is now we can adapt to all of those. But what would happen if we took our 4:3 game design screens and displayed them at a widescreen resolution? For example, if we plugged in 800 by 450 into our resolution settings for the game, while yes, draw scaling is still in effect and fitting everything to the screen, the problem is in order to fit it, there is some stretching taking place.
Yeah, everything looks kind of squashed down, vertically speaking.
So in actuality, our code is doing exactly what it's supposed to. It's taking that internal render target texture and stretching that to fit the screen.
Yeah.
The problem is with the aspect ratio, that stretching becomes apparent to the eye. We now notice the word main is stretched out, especially this log text here on the bottom.
Right.
So in order to deal with different aspect ratios, what we need to do is come up with a way to mathematically maintain our game's original aspect ratio. Now, in order to fit this aspect ratio onto a screen of differing aspect ratio, we'll have to apply black bars, either horizontally or vertically, depending on the aspect ratio change that's taking place. For example, if you can imagine this screen simply being squashed in, so if we added some black on the left side and the right side, we'd bring our whole screen in, and that would patch everything up. So what we need to do in this lesson is find the math necessary to adjust our draw scaling. Let's take a quick look back into our game. And up here in nDraw, we've created this destination rectangle, and later we use that to draw it to the screen. What we're going to do is put a little bit of code in between here to look at the screen and fixed aspect ratios, and then modify this destination rectangle appropriately so we draw to the correct size.
So it fits either into the width or height based on the appropriate setting from your aspect ratio.
Exactly. So
basically, you'll get black bars horizontally or vertically. And the cool thing is the black bars are already there because we set our graphics device clear to color black.
Exactly. So, to begin with, we're going to need the aspect ratio of our fixed drawing resolution and the aspect ratio of our screen. So I'm going to make two double precision floating point numbers here stored as local variables. So we'll have double fixed aspect, and we'll set that equal to our fixed width divided by our fixed height. So we're going to get the actual aspect ratio value by simply dividing the overall width by the height. So that is global state dot fixed drawing width divided by global state dot fixed drawing height. Now, one thing to watch out for here is the fact that since both of these are integers, we're going to truncate on any remainder that might be present. So what we'll do is we'll make sure that we cast one of these to a double beforehand to make sure that all of the arithmetic takes place here using double precision floating point numbers. And I'll also drop in our equal sign so we assign that over to the variable. Now we need to do the same thing for the screen aspect. So we'll jump in here and we'll make a variable called screen aspect.
And this is the aspect ratio of your output, whatever that happens to be.
That's right. And the output, we can gather that size by looking into the presentation parameters and looking at the back buffer width and height. As a matter of fact, we can just steal this back buffer width and drop that over here. So we've got presentation parameters dot back buffer width divided by presentation parameters dot back buffer height. Actually, with a little bit of spelling.
That was awesome. I don't know what you just spelled, but it was great.
But there we go. Patch that up, and now we have our fixed aspect ratio and our screen aspect ratio. And it's when these two differ that we need to look at doing some correction, adding some vertical or horizontal bars. The first we'll address is vertical bars, meaning that the aspect ratio of the screen is higher than our fixed aspect ratio. For example, 4:3 gives an aspect ratio of 1.333 and then continuing. whereas 16 by 9 gives an aspect ratio of, if I remember correctly, 1.777 continuing.
Yeah.
So that widescreen 16 by 9 aspect ratio is indeed higher than 4 by 3.
Right. And 16 by 10 is like 1.6 straight up.
Right. And so we'll use these to decide where the black bars go.
See, I'll do the easy one, because you're just dividing by 10.
Very nice. I didn't even think about that until just now. Very cool. But anyway, we'll put together an if statement, and we'll first look for the screen being a higher aspect than the internal render target. So if we look at our screen aspect, and that happens to be greater than our fixed aspect, then we know that our screen is wider than our game, and we need to add black bars on the sides, so vertical black bars. Now at this point, we need to, it would help to get a little bit better of a visualization of exactly what we're trying to do, because we're trying to squash the screen into a widescreen view, but still maintain as much resolution vertically as we can.
Mm-hmm.
So to make all of that easier to explain, what we've got here is a small demo which should work well as a, you could say, an interactive whiteboard.
Okay.
We've got two rectangles, and both of them are measured. The outline rectangle will represent the screen, and the picture rectangle will represent our game.
Now, just so you guys know, this is a real treat you're getting here, because this is a program Logan wrote just to prove this point.
Exactly.
I thought it was pretty impressive.
That's true. This program has no purpose in existence except to demonstrate aspect ratio. But also noting that you can take either of these items and easily move them around. So as we adjust our screen aspect, you can see that we're also seeing what resolution that would account for.
So the rectangle on the left is going to be representative of our actual output monitor,
right,
being a TV screen or our computer screen or what have you. And then the little picture of the kitten on the right, that's going to be representative of our game screen.
That's right. So let's put together an example scenario, because the whole thing here is, even looking at this, if I size up the cat image just a little bit more, let me up this to maybe, just playing around a little bit so we get this text a little bit more readable. You can see we have 1.333. If we look back at our convenient legend over here, 4x3 is indeed 1.333.
Mm-hmm.
Of course, longer if we were to calculate the full precision. So let's say that we wanted to fit this image into a screen and maintain aspect ratio. For example, since we have 4x3 here, let's make our screen a resolution of 640. And need to scale this out just a little bit more. 640, there we go, by 360. So something like that. And if we move the cat image out of the way, we can see that that gives an aspect ratio of 1.778, matching our 16 by 9 aspect ratio. So here's an example of a high-definition television.
Sure.
So if we're trying to fit our game into that, what do we do? Well, we know that we can fit vertically, since we're going to be adding vertical bars on the side. So let's, right off the bat, scale our cat image so that its vertical resolution matches the screen resolution at 360. Right. Now you notice in doing this, we have now skewed the image, because we kind of squashed it as we scaled it up.
Yeah, our cat's a little tall.
So what we need to do is simply widen the image until this aspect ratio clicks back into 1.333. So here interactively, we can do that very simply by simply slowly dragging until we get 1.333. So very good. Now we have an image that does indeed fit on the widescreen area, while it itself is still 4x3.
Right. So now we just need to center it up.
Right. So now the only thing that would be left would be to take the space over here, cut it in half, and put half of that space over here on the left, or
move it half as far.
Or just do that.
Yeah.
So that's the operation we need to do. Now we do need to describe this operation mathematically before we can put it in place in code. So what we'll do is we'll first note the value that we can get most easily is the height of the image. In any case here where we're looking at the 4x3 going to a wider aspect, we're going to match the height of the display.
Right.
So that means our drawn image is simply 360. We'll just match that. The width we need to gather is going to be this bottom width. Where does 480 come from?
Okay.
Because we need to take into account our height and our aspect ratio proportionately, since the aspect ratio describes the relationship between the two. So really all we have to do is multiply our height by our aspect ratio to get our width. And we can prove that very briefly here in Calculator. If we simply take 360, which we've gathered from the height, multiply that by 1.333. And we'll see that is 479.88. Now again, I didn't go to the full precision of that aspect ratio,
Right.
but that's
That would be
very
480.
close to 480.
Yeah.
But that's the math. Find the height, multiply that by the aspect ratio, and that should give you the width.
Well, in any case where your aspect ratio is larger at the output than it is on your internal, then you're always just taking whatever the height happens to be.
Exactly.
So whatever the height of your output is, that's going to become the height of your output. Oh, did I say that right? I don't think I did.
The height of the output becomes the height of the output?
Yeah, the height of the output is what you're going to use to size up your rectangle.
Right.
That's what I meant to say.
Well, now that we've seen this in place in the interactive demo, let's put this into action in code. So back here in the drum game, now that we've got an idea of the kind of math we need to do, I'll even drop down a little comment to keep these two straight. We're going to say that we will add vertical bars. So now we can jump in, and we need to find that new width. Since we know that, so just thinking about it, height is going to be this guy exactly. Presentation parameters are our screen. Back buffer height is the height of our screen. So there is our height value. And you'll note that that's already the destination rectangle we're storing, so we're simply not going to worry about that. We'll note that because of the destination rectangle, we already have a little bit of that done. That was done in the interactive. We already have the height lined up. We just need to pull the width back into something that matches. So that means we're going to need to take our destination rectangle. We will address its width. And we need to set that width to be our overall height times the aspect ratio, just like in the demo. So we can look at presentation parameters dot back buffer width and multiply that by, where's that? Oh, excuse me, I was
Back
looking at the
buffer
wrong
height.
thing. I knew that sounded wrong. So
We're already working on the width.
and that's the whole point of the visual demo. Is like I don't think we measure width in up and down.
Another way that I try to remember it is if you're going from a smaller aspect ratio to a larger aspect. So if you're stepping up, you want to scale vertically. If you're stepping down, scale horizontally. And what I mean by that is that's going to be the measurement you take first.
Right. In this case, our first measurement is already in place.
Right.
So now we need that second measurement, their width. And so that'll be the height times the aspect ratio. So in this case, we want to multiply the new height by the fixed aspect ratio. And another thing we want to take into account is that this arithmetic, because the fixed aspect ratio, is going to be done as a double. So we're going to cast the result of this back to an integer after we do it. So we'll make sure that we put the entire operation into parentheses and then cast that result over to an integer before we store it in width. And another way to look at this is that it's almost like saying we've got fixed aspect, that's the aspect we need to stay at. And this is our size in screen dimensions, so make screen dimensions be adjusted to be fixed aspect ratio.
Okay.
So at this point, we should be able to run the game, and we'll note that the aspect ratio is indeed corrected. We now have our screen drawing within the new resolution, and we've got a black void taking up the remaining space. We just need to center things up now.
Right.
So in order to center everything up, we'll just move the destination rectangle over in X. So we'll take our destination rect.x, and we will set that equal to
half the distance, or would that be half the width of that black space on the right?
Right, it's actually going to be half the overall screen width. That would give us a point in the center of the screen, minus half the width of our actual drawn rectangle.
Okay, so yeah, because you have to base it all off entire screen size.
So yeah, just the basic premise of centering one rectangle on another. So we'll take presentation parameters dot back buffer width divided by 2. Again, that gives us the center of the screen. Now we need to offset to the left to take into account the fact that we're drawing from top left when we go to draw this rectangle. So we will subtract destination rect dot width divided by 2.
Cool.
Now if we run, there we go. We now have the black bar calculation taking place. We have our fixed aspect ratio for our screen, even though the screen resolution is now different.
And the letters still look good.
Amazingly so, because they're getting even smaller. Because if you think about it, now we're dealing with, and just for the fun of it here, right before we go in to draw it, let's set a breakpoint and find what that new resolution actually is. Our destination rect is now 600 by 450.
There you
Because
go.
remember, the screen res is 800 by 450, but we can only use up to 600 pixels of that in width if we're going to maintain our aspect ratio.
Very nice.
So The next thing we need to tackle is what would happen if our screen were taller than it was wide, or even just taller than in aspect ratio, not even necessarily taller altogether. For example, if
that would mean you're stepping down to a smaller aspect ratio.
Right, because now our screen resolution would be smaller, so we'd have to do, like you said, a step down.
And a funny little mnemonic, if you actually need to use it, is if you're going up in your aspect ratio, then begin by scaling vertically, like standing up. And then if you're stepping back down, then begin by scaling sideways, which is like lying down.
Okay, I see. Standing up or lying down. But in this case, let's see. Let's find an aspect ratio to test, or excuse me, a screen resolution to test for a narrow aspect. Let's just see briefly if 800 by 800 will fit on the recording screen.
Sort of, not really.
Not really. So let's bring it down a little bit, and let's see here. Let's do, I don't know, 600 by 600.
Yep, that'll fit.
There we go. So even though what's funny is technically this is indeed a square, but we're so used to looking at applications and monitors in 4x3
it looks weird
that you can even at this res you can tell everything is getting kind of scrunched in. So we know we need to come up with some kind of mathematical calculation because we're going to be squashing something into something else. But to lock some of those terms down, let's go back to the interactive demo. And let's actually go through here and pull this back on screen.
There he is.
And if you're wondering why everything decided to wig out and go crazy, it's because this demo doesn't take focus into account.
So basically he's been moving that kitten around the whole time he's been working.
Exactly. Now, for the sake of our opposite aspect correction, let's make an example screen that is narrower than it is tall.
You make 4x3. Actually, something that is narrow. Okay.
So let's do something like 360 by 440. There we go. So an obviously narrow rectangle, and that gives us a crazy aspect of 0.0818.
Now, granted, even though like a resolution or a screen size like that is fairly impractical, this exact same calculation will work if you have a wide aspect ratio, like a widescreen style game that you're taking down to a standard 4x3.
Exactly.
It's the same math.
In any case where we step down in aspect ratio.
Exactly.
Because we're even going to show that because we're using an obviously narrower screen here while we're using a square screen to test inside of the game.
So we're just we're pushing the example a little bit further than you'll normally see it.
Exactly. So let's go here and just try dumping the kitten image into the screen. Now the first thing you'll notice is that we'll probably want to match in width, not in height. Because if we tried to match in height, we'd end up with something like that. So I mean, obviously that's not working. Even if we tried to fill it full, well, we're obviously still too narrow in height, so we're going to need to bring it down by some amount.
And so it's like that, again, that little, I don't even know if technically that's a mnemonic, just a way to remember something. If you're stepping down, then begin by scaling horizontally, kind of like lying down.
Right. And using the power of the interactive one, we can even do just this. So let's fill the screen with the cat image, and then simply step down, like you said.
Yeah, until we find the aspect we're looking for.
So now we'll just watch the aspect of the cat image. And as we're dropping down, we're getting closer and closer to 1.3, and there it was. There we went past it, 1.333.
Gotcha.
So, of course, then all we need to do is center up horizontally, something like so, and we would have our calculation. So, mathematically, what does this mean? Well, let's bring up the calculator and do a test. As a matter of fact, before we bring up the calculator, the idea here is that we can find the width immediately. We just match the width of the screen. That means this number down here, this 360, is already known. We already know it because it's what the screen is set to.
We just need to know the height.
Now we need to gather this height value. Where did 270 come from? And we can gather this by simply dividing the width by the aspect ratio. So if we divide 360 by 1.333, so we can bring up a calculator and do just that, 360 divided by 1.333 gives us a value of 270 dot some numbers. Again, we're not doing this as accurately as we are with the double variables inside of the game. But again, that's a calculation. It's as simple as taking our width, dividing by the aspect ratio, and that gives us our height. And then the only other difference is we're centering in Y instead of centering in X. So let's jump back into the game and code the rest of this in. So back to the game class. Let's make an else if clause for our if statement. We'll say else if, now we're looking for the other way. if the fixed aspect is greater than the screen aspect, or to make it follow what you were saying, if we were stepping down, we could actually write this the other way. We could say that if our screen aspect is less than or lower than our fixed aspect, then we're doing just that. We're needing to do that step down.
So you're flipping your little operator as opposed to the two factors?
Exactly, just to make it flow with the explanation so far. And in this case, of course, the bars are going to appear on the top and bottom, so those will be horizontal bars. So we'll be adding horizontal bars. And now the calculation, again, we're looking at modifying the height of our destination rectangle. So we'll take dest_rect.height, and we know we can gather the height by taking our screen width. So again, presentation parameters.backBuffer width should be our screen width. And now we need to divide that by the fixed aspect ratio. Of course, this is a floating point, so we'll do the exact same thing. We'll run this entire operation in parentheses, get the final result, and cast that result to an integer. And then we can safely store it into destination rectangle.height. Now we can immediately jump in and we'll do our centering as well, since we'd already seen that in the previous example. Destination.rect.y, so centering in y, will be equal to presentation parameters dot backBuffer height divided by backBuffer height dot 2 will give us the center in y. Then we'll offset or subtract destination rect dot height divided by 2. And then we should have the two rectangles centered on each other. Now if we run, there we go. We have maintained our aspect ratio, and we are getting horizontal bars across the screen.
Very nice. That makes it real easy to understand.
So in that case, you'll also note that there is no else clause, because the else in this case meant
would be if it was square.
Would be if it was, or not square, but equal.
Well, yeah, equal to, excuse me. That's right. If it was actually the two aspect ratios lined up properly, in which case we don't need to do this modification to the scaling anyhow.
Exactly, because they match, which means filling the screen is exactly what we would want to do, and then we would need no modification to the destination rectangle.
It's actually funny you mentioned that. Is like while you were typing, I was like, but, there's no final. Oh, never mind.
All right, since we've tested both widescreen and narrow screen at this point, and like you were saying before, the same calculation applies to any screen resolution you might have, because we've got all three possibilities accounted for. Things being the same, aspect being greater, and aspect being less than.
Yeah, and when stepping up, you basically start off with the height. When stepping down, you start off with a width.
Now, before we end off, I do want to go back into our configuration and make sure that we set our resolution back to the recording res.
So the really wonky default res.
Just to get everything ready for any future videos. So again, we'll jump into the game, and now everything is drawing back as it was originally, making best use of this 4x3 screen that we're recording on.
Very nice. So it's a really nice supplement to our scaling system, and I believe that's going to wrap everything up for this video.